There are two more functions that we'll need to cover. One is an exponential function and one is a logarithmic function. And they're very special functions because they have a special base, the base e. So exponential functions to the base e, where e is an irrational number, it's not quite the value of 3. We need to think of e and use e like we do the number pi. Pi is an irrational number that we are comfortable with now. We know it has to act like any other real number. We can simplify it to 3.14. We can use more decimal places if we want to. But you can see that e is roughly the value of 2.72, so it's not quite 3. So if you're doing something with the base of e, you can think of how would 3 behave. That's pretty much how e is going to behave. But they play an important role, the base of e does, in exponential functions and logarithmic functions, both theoretically and in applied mathematics. So we will see the base of e for exponential functions and logarithmic functions a lot, especially when we get to calculus. So let's talk about the graph of the natural exponential function f of x equals e to the x. E to the x is positive, just like we said. It's not quite, e is not quite a value of 3. So however 3 to the x behaves, e to the x is going to behave similarly. So let's look at inputs and output values. Just like the other exponential functions, when we put in 0, e to the 0 is indeed 1 because e is a real number, and any real number raised to a value of 0 has an output of 1. When x is 1, y is roughly 2.72, and so on. We can see that we just take that base of e and we square it, or we cube it, or we put it in the denominator of a fraction, and that's where these outputs come from. So graphically, we shouldn't be surprised that it looks a whole lot like the graphs that we looked at for f of x equals 2 to the x. It is an exponential function. It has a domain that's negative infinity to positive infinity. It has one y-intercept, which is the point 0, 1. It has the horizontal asymptote that is the x-axis, or the line y equals 0. It is strictly increasing everywhere over its domain. So everything that we saw in our last lesson for 2 to the x, that's true here for e to the x. The base is just a different value that's not quite 3. And this is called the natural exponential function. Now, something that we didn't talk about for exponential functions and logarithmic functions are the fact that they are inverses of each other. First, let's talk about the graph of 1 over e to the x, or e to the negative x. Because we looked at 1/2 to the x, we're going to see that 1 over e to the x behaves similarly to that function. It reverses the relationship for the positive and negative inputs and is basically a reflection of the graph of e to the x over the y-axis. We can see, just like the other exponential functions whose base was between 0 and 1, it's a strictly decreasing function, still has the 1 y-intercept, still has the same horizontal asymptote, and is very large in quadrant 3, never touches the x-axis, but as x gets larger and larger and larger, the outputs get smaller and smaller and smaller, but stay positive. So what I was talking about a minute ago is the logarithmic functions and the exponential functions are inverses of each other. Here is a logarithmic function that has base e. We normally write the natural log function just as ln x, but understand that is like writing log to the base e of x. This is the shorthand that we use for the natural log function, but it is a logarithmic function to base e. And it is, you can see from the graph, a logarithmic function. It has the same point our other logarithmic functions do that we saw. It goes through the point 1, 0, so it has one x-intercept. It doesn't touch or cross the y-axis. The y-axis, or the line x equals 0, is a vertical asymptote. It is strictly increasing, so much like log base 3 to the x, it looks much the same, except its base is not quite 3. It's just a little bit smaller, as we just discussed. The value, sorry, that should be a 3. The value of e is 2.72. So from the graphs, if I was to graph y equals e to the x and then graph y equals natural log to the x, they are direct reflections of one another over the line y equals x. And graphically, we know that that is always true for any set of functions that are inverses of one another. If we can take any point on one function and reflect it the same distance perpendicularly across that line y equals x in the plane, and it maps us to a point on the other function, then these two functions are indeed inverses of one another. We know analytically if functions are inverses that when we compose them and we get mapped back to where we started, then they are indeed inverses. So if I take e and I feed it the natural log of x, e to log based e of x does indeed give me x. So it mapped me back to my initial input value. If I take the natural log function or log based e function and I feed it e to the x, I will indeed get x for an answer. And that's what I need in order for functions to be inverses of one another. They undo each other and map me back to where I started. So graphically, these are inverses. We can tell by looking at the graphs, and we can tell analytically that they're inverses of each other. They are mirror images of one another over the line y equals x in the plane. I'm not going to take time on this video to talk about transformations of these functions because they are exactly the same that we saw in yesterday's lesson. If we move things to the right, that is inside where x is, and it's going to be minus some value. If we move things to the left, it's inside where x is, and it's going to be plus some value. We can do that for e to the x. Either way, there's horizontal translations to the right or to the left. We can do it for natural log. So everything that we learned for these transformations or reflections are still true. If I want to, I'll find a different color here. If I want to take the e to the x function and move it up or down in the plane, I would just add or subtract a real number. Same for the natural log function. I could move it vertically up or down in the plane. If I wanted to reflect over the x-axis, it would look like that. If I wanted to reflect over the y-axis, it would look like that. So the transformations that we know are the same as they were for the other exponential and logarithmic functions that we just dealt with. So let's look particularly here. I want to make sure that this is in your notes. The properties relating e to the x and natural log of x is that they are inverses of one another. If I compose them in either direction, it will map me back to the original domain input value that I started with, and that means that these functions are inverses of one another. So make sure that that's in your notes and that you understand analytically this is what you would have to show to prove they are inverses. Graphically, you just have to show that they're reflections of one another over the line y equals x in the plane. So that's it for this lesson. Come to class next time and we'll work some homework problems.